Today we start with part 6 of this series on Newtonian gravitational force, and today's video is about energy and its conservation. Now in video number 4 we explained how we reduced the two-body problem we had into a one-body problem, where now we have just one object of mass called the reduced mass and located at position R. So now the point is, how do we study the motion of such an object? We will talk about the fact that gravity is a conservative force. Now if you look at the direction of force of a gravity, it is an attractive force. So the direction is opposite to R, toward the center of the force. And because of this, force of gravity is one example of what's called central forces. Central forces are forces that are directed along or opposite to the position vector or the radius vector R. And also their magnitude only depends on the distance R. So they have a spherical symmetry. So force of gravity is an attractive force that is also a central force. And we know that for all central forces, they are conservative forces. Mathematically, we can prove that force of gravity is conservative by using the curl operator. So the curl operator acting on the force, we could prove it to be zero. And we could also find different ways to prove that, but it's a well-known fact that gravity and all central forces are conservative forces. Now what does it mean, conservative force? There are different ways to say that. A conservative force is a force in which its work is independent of the path taken by the object, which means that if you start from one point and you finish at another point, no matter how the object moves between the 2 points, always the force of gravity will do the same work. So work will only depend on the initial location and the final location. There's the details of the path itself is immaterial, is not important to find the work of the force. So the force is only dependent on the initial and final location. Now what does this mean? Now since the work is only dependent on locations, initial and final, because of that, we could define a function, a scalar function, that's called the potential energy field, which is a scalar field. And this is a scalar field that depends on locations. So now we can relate the potential energy to the work and to the force itself. Mathematically, we say the force of gravity is defined to be negative the gradient operator on the potential energy U. So U is the potential energy, which is a function of coordinates, and the force is defined to be negative, that's opposite to the gradient operator acting on the potential energy. The gradient operator is a vector operator, and it is also studied in mathematical physics, in mathematics, and many students at the university level should be aware of that concept. Now, how do we relate? How do we find potential energy? So, to find potential energy using some mathematics that's studied in vector calculus, we can prove that. If you have 2 points, initial and final, so the potential difference between the two locations is related to minus the work of the force, which is conservative. So notice that first, there is a negative sign in the definition, and that's related to the way we define the force to be opposite to the gradient operator acting on the potential energy. Now, the direction of the gradient operator acting on the potential energy is always in the direction of maximum increase in the potential energy. And so, by definition, the force of gravity is opposite to that. So that means, physically, if the object is moving along the force direction, it's going to lose potential energy. If the object is moving away from the force, it will gain potential energy. So that's the meaning of that's one way to understand the meaning of the minus sign. Now, to find the potential energy itself, we use the formula that the change in potential energy, U final minus U initial. So initial and final are just two locations. So let's say the object was located initially at some point, initial point, and it goes to another location that's called the final location. Now, the difference or the change in potential energy is related to the work of the force with a negative sign. And that negative sign simply coming from the definition above. So, the change in potential energy is simply minus the work done by the force. Now, physically, the work of the gravitational force is related to the change in potential energy, not to the absolute value of the potential energy. So that means really what matters in physics is not what is the potential energy absolutely at any point. All what's really important is the difference, that's the change in potential energy. And that's why many times when we try to calculate potential energy, we tend to locate one point in space, and we call it the reference point, at which we measure potential energy relative to that point. Usually when we talk about or when we study motion of big objects around the sun or around Earth and so on, we tend to take that reference point to be infinity. So our initial, we take it to be at infinity, at very, very far away from the center of the force. In that case, you can prove that the potential energy at any other location is minus capital G, the universal gravitational constant, multiplied by the two masses, mass 1, mass 2, divided by the distance r. So we notice that the potential energy depends only on r, the distance, and so it has a spherical symmetry. And the other thing is, it's negative quantity. Now, what does it mean, negative quantity for the potential energy? It simply says that relative to the reference point, which is at infinity, then the potential energy at any other location is less. Now, notice that at r goes to infinity, the potential energy tends to go to zero. So that means at any other location that's closer to the center of the force, the gravitational potential is less. So it's minus, or it's a negative quantity. As we go away from the origin, the potential energy will increase. As we go to very far away distance, it will tend to go to zero. As the object is moving closer to the origin, the potential energy is decreasing in value, more negative. Now, instead of carrying the three constant, capital G, mass 1, mass 2, just combine them into one constant. We just call it K, just to simplify the notation. So we can just say the potential energy at any location R is just minus a constant, K divided by R. Now, just want to make another note. Sometimes when we deal with objects moving close to Earth, to the surface of Earth, we would like to take the reference point at a different location, and that's usually the surface of Earth. So we define the reference point to be the ground, where we said we will take the potential energy at that location to be zero. Same concept will hold. As we move away from the surface of Earth, go up, the potential energy will increase, and as we go down closer to the surface of Earth, potential energy will decrease. So, for using conservation of energy now, if you think about any object moving under gravity, it will have two types of energy, kinetic energy and potential energy. The sum of them, that's what we call the mechanical energy E. And conservation of energy says that this quantity should be conserved. That's a constant of motion. It doesn't change with time. Now, kinetic energy is just half the mass times the speed square, and the potential energy is minus k over r. So the sum of the two terms, that's the total energy, should be constant and conserved. Just to remind you, since motion is in two dimensions, as we explained in an earlier video, so in two dimensions, the velocity in general has two components. One component will be radial along the radius r, and another one will be perpendicular, that we call the rotational component. So velocity will have two components, radial component and a rotational component. The two components are perpendicular to each other. Now you may think, what are the possible values for energy in such case? Well, because energy is just the sum of kinetic energy, which is always positive, and potential energy, which is always negative, so then the total energy could be positive, could be zero, and could be negative. That would simply depend on whether kinetic energy is bigger or smaller or equal to potential energy. So in general, total energy could be positive, could be negative, and could be even zero. Now think about it. For the case of positive energy, the kinetic energy will overcome the potential energy to make the total energy positive. Now in this case, the object can move far away, can leave the center of gravity, because as r goes far away, r becomes so large, the potential energy is approaching zero. But since energy is positive, so the object will still have enough kinetic energy to keep moving. And that means the object can leave the center of gravity, and we say that the motion is unbound. Unbound means it's going to leave the center of gravity. The same conclusion will hold also for energy equal to zero, because as the object far away, its potential energy is approaching zero, the object still will have little speed that also will be approaching zero at infinity. So the object will leave the system, but with very small speeds that's approaching zero. Now the more interesting case, if the total energy is negative. Now in this case, the object can never leave the center of gravity because its kinetic energy cannot overcome potential energy. So as the object is moving far away and its potential energy is increasing in value, that's approaching close to zero, the kinetic energy cannot overcome that, and at one point the object will stop and then it will come back toward the center. So for energy that's negative, we say that motion is bound and the object can never leave the center of gravity. Now we finished the video with one question asking why Earth doesn't fall and smash into the sun. Same question will go, of course, for other planets and many objects moving around the sun. Well, the answer really lies in the conservation laws of energy and angular momentum. So let's answer this question in general. Yes, sometimes that happens if angular momentum of the object, which is constant of motion, is equal to zero. In that case, the velocity of the object and the radius r are parallel or antiparallel. So now it's possible for the object to move on the radius, along the radius, in the direction of the center of gravity, and eventually it could hit the sun. So that could happen. However, if the angular momentum, which is constant of motion, is not zero, then that means the object is having a rotational component of velocity. Now we find that as the object comes closer to the force of gravity, to the center of gravity, its rotational velocity becomes so big that its energy, the kinetic energy coming from rotational movement, becomes so big that it will overcome the decrease in potential energy. And because of conservation of energy, then the object will move to some distance, and then it cannot go any closer to that, and that it will go back far away from the center of gravity. So really it's due to conservation of angular momentum, and conservation of energy will prevent Earth from falling into the sun. Thank you for watching. If you have any questions, any comments, please write them down in the comments section. Thank you.